Okay, this is section 1.7. These blank notes are on Moodle. So in this section, we're going to first look at sets and different ways to describe sets. It's not exactly in your book, but it's something that I want to make sure everybody's clear about. Because if I didn't go over, I know that you would probably have questions. And roster notation and inequalities, we'll make sure we're all clear on what all that means. And interval notation. Then we'll look at what is relation. What is a relation versus a function. Domain and range, vertical line test, and then function notation last, which is really the most important thing. Function notation right there, okay, which you will get practice using for the rest of the semester. Okay, so first let's look at sets. There's two general sets of numbers. One is called the integers. Actually, there's more than this, but these are the two commonly used ones. Integers are all the whole numbers, positive, negative, zero, everything. They are whole numbers, countable numbers, you might say. And they can be positive or negative. So all the way from, negative infinity, negative a million, let's just put ... Negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and on forever. Okay. Real numbers, as opposed to integers, real numbers are the same except they include all the decimals and fractions that are in between all of these integers, as well as the integers, right? So any number that you pretty much have ever dealt with is real. There are what's called imaginary numbers that involve what we call I. Okay, so not imaginary numbers. Some of you may have used this. I is the square root of -1, which doesn't exist. If you try to type that in your calculator, you'll get an error because no number times itself equals -1. But just any decimal fraction, everything. So just some examples, right? -500, negative 22.4. You might have a repeating decimal, 5.3 repeating. Might have fractions, 17/4. Irrational numbers like pi or e. E is a 2.718. We'll get to that. Okay, all those numbers, all the way from negative infinity to infinity. A set is just a group of numbers. Really, more generally, it's a group of objects, but in math, it's a group of numbers. Elements are members of the set. Okay, some sets have a small, countable number of objects or numbers in them. That's finite. If you can count it, even if it takes you forever, if you can count the number of objects in a set, it's finite. It's a countable number of elements, as opposed to infinite, which has infinitely many elements. So if you have infinitely many elements or objects in a set, you can't list them all out. Okay. All right, so why did I explain all that? I'm going to use all these words as we go, okay? If a set does have a finite number of elements in it, it's kind of the opposite of what I said about infinite sets, then it can be described in roster notation, which means you list everything out. In roster notation, you always put little curly braces around everything. For example, the set of billiard balls between 1 and 15 can be listed out. And you just, in roster notation, you put commas between everything. It's okay to use the little ellipsis if there's a pattern, as here there's obviously a pattern. Okay, that's roster notation right there. It could be a smaller set, like I think in class we did 4, 5, 6 or something. There you go, you just list them out. So roster notation can only be used if you can list them all out. Let's try this. There we go. Okay, infinite sets, where are we? There we go. Infinite sets can't be listed, but they can usually be described with an inequality or in interval notation, which we'll do next. Okay, so an inequality, I'm sure you've seen this before at some point. That you have to have a variable, so let's just use x. Okay, say we want to describe the set of real numbers that are between 1 and 15 as an inequality. Well, if I'm talking about real numbers, that means all the decimals and fractions and everything that are also in between all of these whole numbers up here. So you can't list them all out, so we'd have to write it as an inequality like this: 1 less than or equal to x less than or equal to 15. You can also draw that on a number line. I'm just going to put 1, 15. Because I am including those numbers, we'd put closed circles, and then we just shade in all the values of x, let's call that x, in between. Okay. As another example, can you describe the set of real numbers greater than 1 as an inequality and sketch it on a number line? So if you're talking about numbers, real numbers greater than 1, that means x has to be greater than 1. I didn't specify greater than or equal to here, so I'm just going to stick with strictly greater than. On a number line, let's put 1. If it's strictly greater than 1, that means all the numbers bigger than 1, but not including 1. So you actually put an open circle, because this indicates that you can get right up to 1, like 1.00000001, right, but not 1. Okay, but as close to 1 as you can get. We'll include all of those real numbers in that set. Another notation type that's commonly used, and you'll use a lot in WebAssign, is interval notation. So an interval is a set of numbers, or I should say it's a set of real numbers that are in between two numbers. It's an interval from one point to another. If you use brackets, that means you're including the endpoints. Sort of like using a closed circle up here. If you use parentheses, those are used to exclude the endpoints. Just like with the open circle right there. So let's describe the set of numbers, or write the set of numbers described by x between 4 and 6 in interval notation. Okay, now I should probably talk a little bit about this. If you're talking about x between 4 and 6, you can read this: x is greater than or equal to 4 and x is less than 6. It has to be both, bigger than 4 and less than 6. If you try to write, just as an aside here, guys, if you wrote something like this, it makes no sense. These inequality signs have to go the same direction, and they always have to go to the left with triple inequalities. Now up here I just was saying x is greater than 1, and to me it makes more sense just to write it like this with the greater than symbol, because you read it x is greater than 1, and that makes some sense. But it never makes sense to have a triple inequality with the signs going opposite directions. Technically it's legal to flip everything around, and write it like this: 6 greater than x greater than or equal to 4. But that's not standard. It's typical to go from smallest to biggest, so left to right. So I would not write it like that, but that's technically okay. Okay, so numbers between 4 and 6. In interval notation, that means you start at 4, and we're going to include 4, so we'll start with a bracket, include 4, and then we're going to go up to 6, but not include 6, so we'll have a parenthesis there. That's it. This means the set of all real numbers between 4 and 6. Okay, pause the video and try to write this set in interval notation. All right, with that set, we're going from -5 to -2, and we're including both of those endpoints, so we'll start there. -5 to -2, including the endpoints. And there's also some more numbers over here, so you can either put a comma, or if you're familiar with the union symbol, you can do that. I'm just going to go with comma. We start at 3 with an open circle, so parenthesis, and then on up forever. So we're going to go all the way to infinity. Because you can never equal infinity, it's standard practice to always use parentheses with infinities in interval notation. Okay? To describe the set of real numbers, all real numbers in interval notation, that's everything from negative infinity to positive infinity. So you would use parentheses from negative infinity all the way up to positive infinity. That's a way to represent all real numbers. That's used pretty often, actually. Another shorthand way to represent all real numbers, just as a bonus thing, is a double bar R. Means all real numbers. You're welcome to use that as well. Let's come back up here. I want to put that over here. Real numbers can be represented with the double bar R. Integers can actually be represented as a double bar Z, like that. So you're welcome to use those. Those are just kind of fun. All right, so that brings us to relations and functions. All this set information will just be used, as we go throughout the course. So for relations and functions, what is a relation? It's just any relationship between two sets of numbers. Okay, any relationship. It doesn't have to be a function. This includes functions and non-functions. Any relationship between two sets of numbers. The set of input values, values that are going into the relation, that's called the domain. That's your independent variable, typically your x. And the output values, the values that come out. So you put in an x, you get out a y. That's called your range. Those are your dependent values, typically a y. That's shorthand for variables there because I ran out of space. So such as y. So let's look at this example. First class stamp rates. In the year 1900, stamps cost 2 cents. In the year 1920, they cost 2 cents. 1940, they were 3. 1960, they were 4 cents. 1980, 15 cents. I remember when I was born, they were about 20 or something, somewhere in this range. And then in 2000, they were 33. Okay, so first let's just list them out as a set of ordered pairs. Okay, as a set of ordered pairs, the first ordered pair is this, 1900, 2, because the year is the input, that's like our x, and the rate is like our y. Because there's a finite number of points, we're not including all the years in between 1900 and 1920, between 1920 and 1940. We're not including any of those things. There's a finite number of points. There's 6 points here. We can list them out in roster notation. So the first coordinate point is 1900, 2, comma, next coordinate point is 1920, 2, 1930, 40, 3, 1960, 4, 1980, 15, and 2000, 33, and you would end it with a curly brace. The domain, that's the set of input values. Well, let me show you what it's not. It's not this. Okay, because when you use an inequality, unless you specify that x is not a real number, you just assume that this means x is a real number, which means you're including all the years and even all the decimal numbers, which really don't make sense, in between 1900 and 2000. So it's not that. Instead, you would actually have to list them all out. The domain is 1900, 1920, 1940, 1960, 1980, and 2000. And the range also is not the set of y's between 2 and 33, because this includes every number, decimal, in between all of these numbers, which are not in the range. So for the range, you have to list them out. Now 2 is actually listed twice, but that's okay. You just only have to write it in the range once. So 2, 3, 4, 15, and 33 is your range. Okay. For this graph right here, the domain and range, let's look at this one. Domain is your x's, your set of inputs. Your range is your output, or your set of y's. So here's the x-axis. Basically, I just go along the x-axis from left to right and list any x values, because this is just a discrete set of points, finite number of points. We're going to list any x values that have a y. Okay, so if we go along from left to right, out here, there's nothing, 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 until we get right here at x equals -2, we do have a point. And then the next one occurs right here at -1, then at x equals 0, x equals 1, 2, and 3. That's our last point. Those are all the x's that are in the domain. The range is all the y's that are covered, essentially here, that have a corresponding x. So I go from low to high along this y-axis and just list all the y's that we have. So going down here, the lowest y that we have is right here at -3, then all the way up through 2. So -3, -2, -1, 0, 1, and 2. Okay, and this graph, that we actually are using real numbers because it's a connected line. So for the domain, you go from left to right along the x-axis and you look for all the x's. Now the way it's graphed, it looks kind of like you only go from -6 to 4. But notice this has arrows, which indicates it keeps going up and out forever and ever. So if this keeps going out forever and ever, then x's go on forever and ever. So the domain is all real numbers, or from -infinity to infinity. And the range is all the y's that are being used. So as I scan this y-axis from low to high, the first y I hit right here is at +4. Let's assume it actually equals +4. And then everything from there on up is covered. We have, in fact, they're all doubly covered, right? Each y has 2 x's, but that's okay. They're all covered, so those are all in the range. A function is a type of relation where the input values are never repeated. Okay, another way, a more common way of saying that is it's for each x, there is exactly, for each x in the domain, there's exactly 1 y. Okay, and this will be made a little bit more clear with some examples. But first let's go actually revisit the problems that we've already looked at and determine whether or not these are functions. Okay, so this one that we just did, for each x there is exactly 1 y. Okay, so when x is, for example, -5, there's 1 y value right there. And as you keep going, when x is -4.5, there's 1 y. When x is -2, there's 1 y. For every single x that I can come up with, there is exactly 1 y. So that one is a function. Okay, this one, for each x, yeah, the same thing here. For each x value, there is exactly 1 y value, for each x that's in the domain. So this one is also a function. Sometimes I write function shorthand like that, fn. Let's see, for the postage stamps. So for each x, when x is 1900, there's only 1 y. The rate was 2 cents. When x is 1920, there's only 1 y. It's 2. Now, yeah, 2 is repeated, but remember the other way of stating that a function is that the input values are never repeated. Output values, or y's, can be repeated. Input values, or x's, cannot. So this one is a function also. I guess that's all we've done so far. So let's go keep looking down here. Determine whether this relation is a function. When the shoe size is 7, price is 35. Only one price for that shoe size. When shoe size is 8, the price is 35. Again, there's only one shoe size. And when the shoe size is 9, the price is 35. So this one is a function. Yes, the 35 is repeated, but for each of these x's, there's only one y. I also want to look at domain and range on this one. I know there's one like this on your homework. On the domain, we only have 7, 8, and 9. That's it. So you'd have to list it out, 7, 8, 9. And the range, there's only one single value in the range. So you just list it like that, 35. Okay. The relation from last name to social security number. So this one's kind of a tough one, but I want you to stop and think about it for a minute. For all the last names in the world, how many social security numbers are there? Okay, let me just use my own last name. It's pretty common. Nichols. For example, my last name is Nichols. My social security number is 1, 2, 3, 4, 5, 6, 7, 8, 9. My husband's last name is also Nichols, right? But his last name, or his social is 0, 1, 2, 3, 4, 5, 6, 7, 8. They're not the same. Okay, so this would be what I'd call a counterexample. This shows that it is not a function because we have two of the same last names with two different social security numbers, right? So this input was repeated, or you could say, you know, for this X, for this last name, there's two Y's, two outputs. So this one is not a function. Think of all the Smiths in the world. Although all the Y's technically should be unique, all the social security numbers are unique. Remember, it doesn't matter if Y's are repeated, it only matters if X's are repeated. Okay, for this set right here, take a look at those X's and Y's. And it looks like all the X's are unique. We have a 2, a 4, a 10, and a 20. It doesn't even matter what the Y's are. The X's are unique, so this one is a function. Okay, and then, oh, this is fun. Let's look at some graphs. Okay, let's look at these graphs. So, and determine the domains and ranges, and then we'll look at, are they functions? So on this first one, it does go all the way from, because of the arrow, from negative infinity to infinity. All those x's have values. So the domain of this one would be from negative infinity to infinity. And the range, this looks like it goes down forever and up forever. So range is also negative infinity to infinity. And it does look like for every single x value, you know, just look at a few, x is negative 4, there's one y. When x is negative 1.5, there's one y. When x is 0, there's one y. When x is 1, there's one y. Doesn't matter what x you choose, there's always one y. So this one is a function. Okay, for this one over here, first let's look at, is it a function, right? For each x, there is exactly one y. That y value is 3. For every single one of those x's, y is always 3. Kind of neat, right? There's always one y. So this one is also a function. Its domain, well, we have arrows and arrows, so domain is all real numbers. And the range, well, when you go along this y-axis, we only have a single y in the range, right? Y equals 3. That's it. So you'd have to list it in roster notation like that. This one is a little bit different. Let's do domain and range first. So as I go along the x-axis, there's nothing, 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 nothing until I get to 3. And that's it. X equals 3 is the only number in the domain. And the range, all the y's that are covered, looks like all the y's are covered as you go from negative infinity all the way up to infinity. So the range is all real numbers. Now for this one, for most x's there's nothing. For the only x value that's in the domain, we actually have infinitely many y's. That's way more than one y. So this is definitely not a function. Okay, and that brings us to the vertical line test. The vertical line test is a way to just graphically look at something, a graph, and tell if it's a function or not. Basically, you imagine a long vertical line like this. Imagine a vertical like a yardstick, okay? And imagine that that line moves across the graph from left to right like this. If you're ever touching more than a single point at a time, that would mean for that value of x, there's more than one y. So that would mean it's not a function. As you can see, as I move this across, I'm only touching one value of x at a time. So that one is a function. It does pass the vertical line test. Now this one, however, I draw my vertical line right here, I'm touching at two spots. So that means for this x value right there, there are two y's. So this one is not a function. It fails the vertical line test. I don't even have to drag it along really great, but it fails for all of those x values. The only x value that has one y is that one right there at the very end. Okay, but yeah, that one fails the vertical line test. Okay. If you have equations, maybe you don't have the graph. You can tell just from looking at it, or I'm going to show you just by plugging in a few points. For any x value that I plug in to this equation, the question is, how many y's do you get? Okay, so let's just plug in one. What if I wanted to plug in x equals 1? Okay, it doesn't really matter what I get, but you get 7 times 1 minus 20, negative 13. I got a single y value, negative 13. That's one y value when I plugged in x is 1. And if I plug in x is 10, you get y equals 7 times 10 minus 20. It doesn't matter what you plug in, you're going to get a single y every single time. So this one is a function because you only get one y for every x. Okay, now this is kind of weird looking down here, but this would be one that's not a function because if I plug in some y's, I don't know, let's just plug in x equals 1. Let's plug in some x's. We have y equals 2 times 1 minus 1 plus or minus 4 times 1. Well, that's 2 minus 1 is 1, plus or minus 4. So 1 plus or minus 4. If I do 1 plus 4, I get 5. If I do 1 minus 4, I get negative 3. So when I plugged in x equals 1, I got two y values, 5 and negative 3, because of that plus or minus. So this one is not a function. This equation right here, 2g squared minus 5g plus 1. If you plug in any g, just pick a random g, let's plug in g equals 0, you get a single w. If you plug in g is 10, you get a single value, right? 2 times 10 squared minus 5 times 10. It doesn't matter what it is. It's a single number. So this one is a function. Okay, check out these graphs. I would probably do these with the vertical line test. Imagine your vertical line here. And then as I drag it across, I only ever hit a single point at a time, which means for each x there's only one y. So that one is a function. However, this one, I hit two y's for most of these x's. So this one is not a function. If you ever hit two y's at any single point as you go along, it's not a function. Okay, if something is a function, then you can write it in function notation. This is really the important part, and the main reason I'm talking about this section is because you need to start getting familiar with function notation. You can write any function in function notation. Typically, you just change the y to something like f of x, and that's it. So this function, y equals 3x minus 5, can be written f of x equals 3x minus 5. Okay, this, whatever you put right there, is the input. That's how you know what to plug in. And then the f, that's the function name. typical function names are f, g, and h, but you can use anything. And then this is called the function rule. It's the formula for it. What do you plug into? So for example, let's find f of 2. That would mean you replace this x by 2. So everywhere over here in the function rule. So that means 3 times 2 minus 5, or 6 minus 5, which is 1. Okay, so that's function notation. It's nice because you can write f of 2. If you wanted to shorten this, you could write f of 2 equals 1. It's another way of saying that when x is 2, y is 1. It's the same as saying the coordinate point 2 comma 1, well, that is a point on the graph. Right, but saying f of 2 equals 1 is the same, you're saying the same thing as you are when you say 2 comma 1 is a point on the graph. Okay? So f of x is basically like the y. When you say f of 2 equals something, that means y equals 1. Okay? If we say h of t equals the height of a rocket in feet, t seconds after launch, let's interpret this statement. What does h of 3 equal 12 mean? So I'd like you to pause the video and try to interpret that as a sentence. What does that really mean in terms of rockets and feet and launching and everything? Okay, this means h of 3 equals 12. This is your input, so that t, notice in the function definition, t is the input. So this means when t is 3, which means if t is the number of seconds after launch, that means 3 seconds after launch. H of 3 equals 12. Well, h of t equals the height of the rocket in feet. Right? H of t equals the height of the rocket in feet. So if h of 3 equals 12, that means the rocket is 12 feet up. Okay. There's several on your homework for you to practice this kind of thing. For this one, let's just find f of 0 and f of a half. Those are two separate questions. When we find f of 0, that means plug in 0 for x. So 7 minus 2 times 0 is 7. F of a half would be 7 minus 2 times a half. 2 times a half is 1, so 7 minus 1 is 6. Okay, say you're finding x such that f of x equals 11. That means we're setting f of x, okay, the y's equal to 11. We're changing that to 11. So we have 11 equals 7 minus 2x. We're trying to find the x such that y is 11, right? So we set the rule, the function rule, equal to 11 and solve for x. So if I subtract 7 from both sides, I get 4 equals negative 2x. Dividing both sides by negative 2, 4 divided by negative 2 is negative 2. So we get x is negative 2. You could also write that f of negative 2 equals 11. Would be another good way to write that answer. Okay, you can read function values straight off of graphs. F of negative 4. Now if you do it, technically you're estimating, but I'm choosing numbers that are clear to read, hopefully. F of negative 4, that means x is negative 4. It means what is y? We're looking for f of negative 4. It means what is y when x is negative 4? So we go out here to negative 4 for x. Well, down to the function right there. Looks like f of negative 4 equals negative 6, because the point negative 4 comma negative 6 is on the graph of f. Or you can go backwards and say, what is the x such that f of x equals negative 2? That means where does y equal negative 2? Well, here's y equals negative 2, and the function is right there. So it looks like when x is negative 1, y is negative 2. Or you could say f of negative 1 equals negative 2. Okay, let's do one applied problem with function notation. The population of Wisconsin in millions is given in this table. Let's let P of t be the population of Wisconsin in millions, t years since 2000. Okay, So let's find an equation for a model of these data using the second and fourth points. And we're going to write the model in function notation. Okay, so the idea is, and we've sort of skipped all this stuff, is that these points, if you graph them, look like they're pretty much on a line. So we're going to estimate this by creating a linear model. There are some really advanced mathematical, I shouldn't say really advanced, but they're somewhat advanced models and statistical models that will get you a really good line that goes through data points without just having to pick 2 points, but we're going to do it by picking 2 points. We're going to use the second and the fourth points to find a model, which means this is my, well, actually it's not quite my x. My x value, or actually we're in t's, that's t and this is capital P. So my t value is years since 2000. So my first coordinate point here is actually 4, 5.51. The second point over here is 6, 5.57. Okay, so if I'm going to find a model, I'm going to need the slope. So I'm going to actually do that up here. Let's find the slope between these 2 points. So change in y's over change in x's. It's 5.57 minus 5.51 over 6 minus 4. 5.57 minus 5.51 is, if you subtract 7 minus 1, you get 6. So 0.06 over 2 is going to be, if you're not sure, use your calculator. 0.06 divided by 2 is 0.03. Okay, now we're going to find an equation for a model of these data. So we've got the slope. We don't have a y-intercept because we're not given any data for year 2000. So instead I'm going to use the y minus y1 equals the slope times x minus x1, and I'm going to just switch over to p's and t's at the end. I'm going to use my first data point here for my x1, y1, and this is my slope m. So we have y minus 5.51 equals m, 0.03, times x minus 4. I'm going to solve this for y. I'm going to add the 5.51 over to the right and distribute the 0.03. So 0.03x. 4 times 0.03 is 0.12, so negative 0.12 plus 5.51 when we move that over. So need to combine these two numbers. 5.51 minus 0.12 is 5.39. So the model is, actually let's not use y's, let's switch over. It would be P of t equals 0.03 times t, and my number was plus 5.39. That is a model in function notation. There. Okay, let's find P of 14 and interpret its meaning in regard to the population of Wisconsin. P of 14 means replace this t by 14 everywhere over here. So 0.03 times 14 plus 5.39. So 0.03 times 14 is 0.42. Plus 5.39 is 5.81. Getting my pen back here. There we go. So I think I said 5.81, yeah. So what does that mean? That's the more important part. So that means the population of Wisconsin, see, T years since 2000. Well, if T is 14, that means this year, 2014. So in 2014, if this model is right, then the population is 5.81 million. Okay, so you should be able to write a sentence. In 2014, the population, let's just leave off the of Wisconsin, is 5.81 million. Okay, And if you go look at the data, it does look like it is increasing, right? Which does make sense also because the slope is positive. So that means it's going up about 0.03 million every year. So if we want to find when P of t equals 5.75, and we already know that in 2014 it equals 5.81, it's going to happen sometime before 2014. Okay, so if you want to, here's our equation right here. P of t equals that. We want to find when does P of t equal 5.75. So I'm going to replace the P of t by 5.75, and then we're going to solve for t. So if I subtract 5.39 from both sides, we have 5.75 minus 5.39 equals 0.03t. So let's see what that number is. 0.75 minus 0.39 is 0.36. So that's 0.36 equals 0.03t. And then if we divide both sides by 0.03, we get 12. T equals 12. So that means it happened in year 2012, the population was 5.75 million. Okay, so that's it for functions, function notation, sets, relations. Okay, so work on your homework to nail this stuff down.